Hello everybody. Today I'm going to explain how to calculate the volume of the excavated soil using Prism method. So let's get started. Okay, so let's say that you have an area and then it should be excavated to a specific formation level for a basement for example. So here is the ground level, and then you would like to excavate to a formation level. So this is the height of the excavation or the depth of the excavation. So we are going to excavate to a formation level, okay, which is the reduced level of the ground here down. Okay, so as you know, it's very easy to calculate the volume. If this area is flat, the volume of the excavated soil would be the area here times the height or the depth of the excavation. So this is based on an assumption that the area is flat. Here the ground here is flat. So if it's a flat, the volume would be the area times the height or the depth of the excavation, this one. So this is the volume. But let's take this example. If you have a sloped area, okay, more complicated topography like this case, so let's say that you've been asked to calculate the volume of soil to be excavated here. So this is the area. It's easy to calculate the area of this shape, okay, but if we take this cross section here, AA, let's have a look here. As you can see here, the ground is sloped, okay, it's not flat. So the excavation, the height of the excavation would be different from point to point. So here, for example, it has this height. Here it's completely different, and here it's different. So we cannot just apply that rule saying the volume is the area times the height, but here the volume would be the area times the average height, from the average height from the ground to the formation level. So to do this, guys, we are going to set out first a grid like this one, and then this is a grid. These are the lines, and we have some intersection points. This is a point, this is a point, this one, okay. And then we are going to do spot heights leveling to calculate the reduced level of each one of these intersection points. So using level, we are going to calculate the reduced level of each one of these intersection points here, the green points. Once we've done that, now to calculate the volume of the excavated soil in this case, we are going to find the volume of this square, let's say, and then the volume of this square, and then the volume of this one, and this one, and then we will find the overall volume in the end. So let's take them one by one. Let's take this square here, okay, to see how to calculate the volume of soil to be excavated here. So this is one square. The volume is the area of the square, okay, times the average height of the excavation. So the average height from the ground level to the formation level. For this intersection point, it's, let's say, h1, here h2, h3, h4. So the average height is h1 plus h2 plus h3 plus h4 divided by 4, and this is the average height. So what is the volume now? It is the base area, the area of this square, which is easy, times the average height, which is this one. Now we've done the first square. Now we will repeat this for the second one. So the volume to be excavated here would be the average height times the area. The area is easy, of the area of a square. The average height is the reduced level, or the height for this node plus the height of this node plus this one divided by 4, and this is the average height. If you notice, guys, now that when we calculated the average heights here, we used this node, yeah, this one. And when we calculated the average heights here, we used the same node again. So we used this node twice, with this square and with this square. Because of that, it would be given a weight of 2. Whereas this node is being used just one time with this square, so it would be given a weight of 1. And this node is being used just with this square, it would be given a weight of 1. Okay, so now this process of allocating weights for each intersection point will simplify the process. It's better than calculating the volume here and the volume here, plus here, plus here, plus here. We can do all the work in one go by allocating a weight for each intersection point. So the weight for each intersection point is the number of times used, as I mentioned. So this node would be used with this square and this square, so its weight would be 2. This node would be used 4 times with this square, with this square, with this one, with this one. Its weight would be 4. So in other words, I can say, okay, to find the weight of any intersection point, just count how many squares around it. For this one, for example, here, guys, the weight of this one, can you tell how many squares around? 1, 2, and 3. So its weight would be 3. Okay, for this one, it would be 2. We have 1 square here and 1 square here. For this one, it would be 1. We have just 1 square here. So these are the weights. Now we found all the weights. The weight of this intersection point is 1, here 2, 1, 2, 4, 2, 1, 3, 2, 1, and 1. So now we have allocated weights for each intersection point. Don't forget our aim. We're doing all of that to get the average height of the excavation. So once we have the average height, we can find the total volume of the soil to be excavated using this rule. So the total volume is the area times the average grid height. So the average grid height is the summation of the weighted heights divided by the summation of the weightings. So the summation of the weightings, guys, is the summation of all of these numbers, 1 plus 2 plus 1 plus 2 plus 4 plus 2, etc. So the summation of all of these numbers, okay, is the summation of the weightings here. The summation of the weighted heights is the summation of this weight times the height of the excavation here at this node. This is called weighted height. So the weight times the height of the excavation here. So the weighted height here is the weight 2 times the height here. So just to remind you, what is the weight what is the height here and the height here. Just if you have a look at this slide here, so this is the height at this node. The height here, h1, times the weight of this node would be called the weighted height. So here h2 times the weight here, it would be the weighted height, etc. As you will see now, it might be better for your understanding to have a numerical example to see how to find the summation of the weighted heights and the summation of the weights. Let's take this numerical example to demonstrate how to calculate the average height of the grid so that we can calculate the overall volume of soil to be excavated. So here in this case, guys, we have an area like this, okay, and then it's required to calculate the volume of soil to be excavated. Using leveling, we have calculated the reduced levels of each node intersection point here. So for A1, this is intersection point A1, this is the reduced level. This is intersection point A2, this is the reduced level, etc. Now let's read the question here. The figure below shows the values of grid spot heights obtained using a level survey. The area is to be excavated to a formation level of 54.550. So this is a very important number. So this is called the formation level. We are going to excavate from the ground to a formation level of 54.550. Now the grid spacing is 10 meters in both directions, so that means each square is 10 meters by 10 meters. So this square, for example, 10 meters by 10 meters here, and this square 10 meters, this square 10 meters, etc. So we have here overall it would be 30 meters by 30 meters to calculate the area. So now we have all the information. Let's get started. First we need to arrange a table like this. Here we have the intersection point and then the reduced level. These values are just the same values from the grids here, just you need to transfer them to the table. So we have for A1 the reduced level is 60.397, as you will see here. So for A1, this is the intersection point A1, the reduced level is 60.397. For A2, 59.713. For A3, this is the reduced level, etc. So we will do this for each intersection point. Just transfer the numbers from the grid given to you here to the table. Okay. So we have here A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, D1, D2, D3, and D4. So here as you can see, A1, A2, A3, A4, B1, B2, B3, B4, C1, C3, C1, C2, C3, C4, and here we have D1, D2, D3, D4, the rest of the table. Okay, it would be one table, but I couldn't fit all of this in one slide. So now, until now, we haven't calculated anything. We have just transferred the numbers from the grid to this table. Now first we are going to calculate the height above the formation level. Do you remember the formation level? This number given to you here, guys, this is the formation level. We are going to excavate the ground level to a formation level of 54.550. So this is the formation level. I will keep it here in front of me. Formation level is 54.550. So the height above the formation level is the reduced level of each intersection point minus the formation level. So this is the formation level, and the reduced level is this number for A1. So for A1, the height above the formation level, it would be 60.397. This is the reduced level minus the formation level, which is 54.550. Okay, and this is the height above the formation level for A1, 5 meters, 0.847. And we will do this now for each intersection point. For A2, the reduced level, this number minus the formation level, this one. This is the answer, and so on. Okay, for A3, the reduced level 59.024 minus the formation level, which is 54.550, and etc. Okay, for each one of them, the height above the formation level is the reduced level minus the formation level, which is this number. Now we've calculated this height above the formation level. Now we are going to calculate the weight or the weighting for each intersection point. Let's go to the grid. So easily, how to find the weight? The weight is just you can count how many squares around each intersection point, how many times each intersection point is being used. So let's start here with A1. What is the weight for A1? It is just 1, because this A1 just 1 square around it, so it's being used just 1 time. For A2, this node, the weight is 2. It's being used with this one, and it's being used with this one, so its weight would be 2. For A3, its weight would be 2. We have 2 squares around. For A4, its weight is 1. We have just 1 square around this one. For B1, the weight is 2. We have 2 squares. For B2, the weight is 4, because we have 4 squares, 1, 2, 3, and 4. So the weight here would be 4. The weight of this intersection point, B3, it would be 4 as well, correct? 1, 2, 3, 4. We have 4 squares. The weight of B4 would be, how many squares do we have around? We have 1, 2, so it would be just 2. The weight of C1, okay, what is the weight of C1? It is 2. We have 2 squares around. The weight of C2, we have 1, 2, 3, 4 squares, so it would be 4. For C3, the same. How many squares do we have around C3? We have 1, 2, 3, 4, so its weight would be 4. And here for C4, the weight would be 1, 2, it would be 2. For D1, its weight is 1. For D2, its weight is 2. For D3, its weight is 2 as well. We have 2 squares around D3, 1 and 2. And for D4, we have just 1 square around, which is this square. So now we have found all the weights. Let's transfer all of these numbers to the table, guys, here. So the weighting, the number of squares around each intersection point for A1, as we have just seen, 1, 2, etc. Just transfer all of the numbers to this table. Now guys, after we have calculated the height above the formation level and the weighting for each intersection point, we are going to find the weighted height. The weighted height is the height above the formation level, this number, times the weighting, this number. So for A1, for example, just this number times this one to get the height above the formation level. In this case, 5.847 times 1, it would be the same. In this case here, 5.163 times 2, okay, it would be 10.326, and so on. So here The height above the weighted height is the height above the formation level, this one times the weight, which is 2, and so on. Okay, so this is the rest of the table. Now once we've completed the table, we are going now to calculate the average grade height, which is the summation of the weighted height divided by the summation of the weightings. The summation of the weighted heights is the summation of all of these numbers here in this column. All of these numbers, guys, should be. We have to find the summation of all of them. Okay, to the rest here. And also the summation of the weightings, we have to find the summation of all of these numbers here, 1 plus 2 plus 2 plus 1, etc. So this is the summation of the weightings. The summation of the weighted height would be 147.788 for this example. So now the average grade height is the summation of the weighted heights, okay, which is this number, divided by the summation of the weightings, which is 36. So 147.788 divided by 36, and the height of the average grade height is 4 meters 0.105. Okay, so now this is the average height. What is the next step? Remember? Yes, the volume is the area times this number, which is the average of the grade height. So the volume of excavation is the total grade area times average grade height. So the average grade height is 4.105, and the total area of the for this example is 30 by 30 meters. So the volume of the excavation in this case is 3694.5 cubic meter. This is the amount of soil to be excavated for this case. Thank you very much for listening.